Okay, so this is the discussion. But before I take on this discussion, let me show you a handy resource that you guys could use. The resource is found in my website, and go to this thing called Fog Links. Go to something called the supplement notes and hint. And these supplement notes and hints are actually, and I've updated it since 2012. I should change that, but it's for your class. But in here, you're going to find the key information that you will need to determine molecular geometry. So all that we talked about last time, naming. Here's the rules for doing Lewis structure. Okay. I will talk to you guys about that today. And then here are examples. This is the key table that you want. We're going to be using this table a lot. Okay, so I'm just going to leave it open to this page. In the meantime, let me tell you a little bit about Lewis structure. Lewis is, like I said, here we have compounds. And in compounds, we can have either ionic compounds, that's where electrons are transferred from one atom to the other. The cation loses its electrons. Those electrons go to an element that wants them. They're the anions. And then through something called Coulombic interaction, electrostatic interaction, they are attracted to each other. Like sodium gets rid of one electron, it gets picked up by chlorine. The sodium is positive, the chlorine is negative, and then they're attracted and they form sodium chloride. So that's your ionic compound right here. Okay, whenever you have two nonmetals coming together, then they don't want to lose electrons. In fact, they want to gain electrons, but they're not going to lose electrons at the expense of the other gaining the electrons. So what they do is they share electrons, and sometimes they're equally shared, and we have something called a covalent molecule. Or they are unequally shared, but still shared in that the electrons are more skewed over to one element versus the other. And this is because that other element has a greater attraction for those electrons. Okay, so this is called polar covalent. So we're going to be concentrating on molecular compounds and polar covalent compounds in this discussion. Okay, so the whole idea of the Lewis structure is that, or when atoms form, is the octet rule. The octet rule is based on the fact that atoms want to lose, gain, or share its valence electrons so that they have the same number of electrons as a noble gas, the closest noble gas. Sodium has one valence electron. It's not going to pick up 7. Okay, it's going to lose 1 to have the same number of electron configuration as neon, rather than pick up 7. The path of least resistance is losing 1 electron. Aluminum has 3 valence electrons. So what does it do? It loses the 3 valence electrons and have the same number of electrons as neon. Okay, and by doing that, it becomes a cation. It's not going to pick up 5 electrons. So again, it's the path of least resistance, and the octet rules are that is simply that. Atoms are going to try and get 8 electrons because 8 electrons are the number of electrons in the valence shell for a noble gas. Helium does not obey the noble gas. I mean, helium doesn't obey the noble gas. It's satisfied with 2. Remember that at most you can put 2 electrons in the first shell. So it doesn't obey the octet rule. It obeys something called the duet rule, D-U-E-T. Okay, but it's still, because the outer shell is filled, it only wants 2. That's why it's a noble gas, because it's satisfied. It doesn't need to lose, it doesn't need to gain. Whenever an atom can do that, then it's stable. Okay, so again, the octet rule is important, and that's the basis of our electron configuration. And here are just some illustration demonstrating the octet rule. Okay, here you see that oxygen has 6. And if 2 oxygens come together, rather than one oxygen losing 2 to another oxygen so that the other oxygen will have 8, and then the oxygen that loses 2 now has 4, that's too much price to pay. So what do? They take these 2 unpaired electrons right here, and they agree to share it, so that now 2 electrons, by the way, equals 1 bond. 2 electrons equals 1 bond. So they agree to share it so that they have 2 bonds between them. But if you look, this oxygen in red has 2, 4, 6, 8 in its outermost shell. This oxygen in violet has 2, 4, 6, 8 in its outermost shell. And by sharing, it now has an octet. Likewise with nitrogen. Nitrogen has 5. So it needs to share 3 of its electrons to get 8 apiece. Okay, that's the whole idea of the Lewis structure. Here is just a review of the valence electrons for atoms. And what you want to remember is that lithium's got 1 valence electron. It needs to get rid of 1. Beryllium has 2. It can get rid of 2. Boron's got 3. It needs to get rid of 3. Beryllium and borons are sort of weird because they're totally happy. Beryllium's totally happy with 4 electrons. It's one of those exceptions. Boron's totally happy with 6 electrons in its valence shell. Okay, so there are always exceptions to this octet rule, and that's what makes chemistry really frustrating for you guys, is that we tell you these rules. Yeah, the octet rules, these are what happens, and then there's so many exceptions. But the general rule is what goes, and then you just have to remember the exceptions. Okay, I apologize for that, but that's just the way it goes. Look at carbon. It's got 4 unpaired electrons. So what can it do with its 4 unpaired electrons? It can share them, and then it can form 4 bonds. Okay, if it shares this electron with another atom, that's 1 bond, 2 bond, 3 bond, 4 bonds. And in fact, carbon generally does have 4 bonds. Here's nitrogen. It's got 5, but 2 of them is already paired. These 3 are unpaired. Nitrogen prefers 3 bonds. Oxygen, there's 6. 2 of them are unpaired. Oxygen prefers 2 bonds. Fluorine's got 1 unpaired electrons. Fluorine then prefers 1 bond. In fact, if you go fluorine, iodine, chlorine, which is down the family, all those prefer 1 bond. Oxygen, sulfur, selenium, down that family, it prefers 2 bonds. And the exercise that I gave you, okay, sort of illustrates the fact that something called periodicity, the elements in the same family have very similar chemical behavior. And so what you should have found out in that exercise is that really doesn't matter what the atom is. All you're really doing is determining the number of valence electrons, and it's the valence electrons that determines the molecular geometry. Okay, it's the valence electrons. Doesn't matter what the atom, as long as that atom has the same number of valence. Like some of you did carbon dioxide, CO2, and I'll show you that shortly here. If you replace carbon with silicon, carbon and silicon have the same number of valence electrons. If you know the Lewis structure for carbon dioxide, you also know it for silicon dioxide. You also know it for germanium dioxide. Why? Because whether you have carbon, silicon, or germanium, they all have 4 valence electrons. And so it's going to have the same type of geometry around it. If you know the geometry of carbon dioxide, you also know the geometry of carbon disulfide. Why? Because oxygen and sulfur are in the same family. So all you do is change the symbol, but you still have the same type of architect. That's the whole idea of that exercise that I gave you, is to show you that you don't have to write the Lewis structure and determine the molecular geometry from scratch. If you recognize the pattern, if you know it for carbon dioxide, then you know it for silicon diselenide, in other words, because the valence electrons in carbon dioxide and silicon diselenide are exactly the same. Okay, so Here's the general rule in terms of the number of bonds these atoms have. So let's take a look at the Lewis structure. Here is hydrogen fluoride. This is the Lewis structure. Remember that one line, like right here, represents 2 electrons. Okay, one line represents 2 electrons. And these pair of electrons here, there's 1, 2, 3 pairs of electrons around fluorine. Well, those are called lone pairs. There are 6 total electrons, but there are 3 lone pairs. This nitrogen right here in ammonia, these 2 electrons right here, that's 1 lone pair, 1 lone pair. Let's see, carbon here has no lone pairs. So lone pairs are exactly that, a pair of electrons that's sitting on an atom. Okay, those are called lone pairs. And 6 electrons will form 3 lone pairs. 4 electrons will form 2 lone pairs. Okay, they're called lone because they are alone and they don't make up the bond, in other words. So again, I'm just kind of illustrating to you that with the Lewis structure, we can determine molecular geometry. Okay, we can determine molecular geometry. So let's take a look at a Lewis structure, carbon dioxide. We already talked about that. Some of you can easily do Lewis structure just based on inspection. Okay, what do I mean by Lewis structure based on inspection? What I mean is that, yeah, it's not. If you take carbon, let's see, if you take carbon right here and oxygen and you sort of, let's see, if you take carbon right here, okay, and you write its valence electron, it's got 4 right here, 1, 2, 3, 4, and you write oxygen and you write its valence electrons. That's why when we learn about elements in the periodic table, I reminded you that you need to know how many valence electrons an atom have. Why? Because it's really the valence electrons that are going to make first contact when chemicals form, and it's the valence electrons that are going to dictate the chemistry. So you don't need to know about the core electrons, that is what's inside the valence shell. You just need to know about valence electrons. Okay, so oxygen has 6, carbon has 4. And what you can do here is that you can actually, let's see if I have a pen. Okay. Well, let's take a look at this right here. You can put a line, you can pair these 2 up right here. You can pair these 2 up right here. You can pair these 2 up right here and these 2 right here. And when you do that, what you have is you can see how the octet rule is obeyed. You have this carbon has 1, 2, 3, 4 of its own, but it's picking up 4 more, 2 from this oxygen and 2 from this oxygen by sharing. Now you can count that carbon as 8. This oxygen had 6, but it picked up 2 more from the carbon because it's sharing. Now it has 8. That's the whole idea of covalent bonds, is that by sharing electrons, those electrons that it shares now belongs to the carbon or the atom that is sharing it. This electron and this electron both belongs to oxygen and carbon because it's shared. So they both have ownership. Okay, so what we do now is we draw pairs of electrons that are connecting 2 atoms as a bond. So what we have is 1, 2, 3, 4. These yellow clouds here, they make up 4 bonds. And then you have these electrons over here that were not shared, and those are lone pairs. So you can see that one oxygen has 2 lone pairs, 4 electrons. Another oxygen has 2 lone pairs, 4 electrons. And so this carbon dioxide molecule has a total of 4 lone pairs in its entire molecule, 4 bonds, And then the total valence electrons is going to be 4 from carbon, 6 from one oxygen, 6 from another oxygen, 12 plus 4, 16. 16 total valence electrons. When you think of valence electrons, think of electrons that are being contributed by all the atoms making up that molecule. Okay, so for carbon dioxide, one oxygen's contributing 6, another oxygen's contributing 6, and a carbon's contributing 4. So there's 16 electrons in the pool. What a lot of students get confused on is that they think that the 4 electrons need to stick with carbon. No, you just take all 16, put it in a pot, and you distribute the electrons so that you obey the octet rule. It doesn't matter where the electrons originate from. You just need to make sure that when you distribute those electrons, each atom obeys the octet rule. That's the key to Lewis structure. That's the key to Lewis structure. Okay, so let's take a look at the best way to do this. Carbon dioxide is easy. Okay, you can do it by inspection. But what happens when you get a very sophisticated chemical? Well, when you have a sophisticated chemical, what I like to do is I like to do something called a bond table. First of all, you guys need to learn how, or maybe it's too advanced, but I will show you the connectivity. Okay, for those of you who have lab, you will see that in the activity next week, I show you how the atoms are arranged. That's the connectivity, which atoms are going to be connected to each other. You guys may not have that experience in you, so we will provide that. Then through this technique, this book doesn't have it, but I've taught from many books, and the best way to do Lewis structure is called a bond table. Okay, if you saw the video that I did in your project, you know what the bond table is. I'm going to do it again here. And then from the Lewis structure, we can just jump into molecular geometry because it's going to be that easy. Okay, but the bond table is going to give you like 80% of your answers in my quiz. The bond table will tell you the total valence electrons. It'll tell you the number of bonds. It'll tell you the number of lone pairs. It'll tell you the number of lone pairs on the central atoms and the peripheral atoms. You really just need the bond table to answer most of the questions. And then you use the bond table to put it all together. Okay, so I'll show you how to do the bond table, and then the remaining electrons are going to be the lone pairs. So let's take a look at this. Carbon dioxide. The way you do a bond table is you write like a multiplication table. You write CO2 right here, okay? And when you write CO2 right there, then you can break down the atoms that make up CO2, 1 carbon, 2 oxygen. And then you put a charge there. Carbon dioxide has 0 charge. It's neutral. So you don't have to worry about that. Then we have 2 columns. One column is called OE, octet electron. The other column is called TVE, total valence electrons. Don't make this harder than it is. Octet electron can only take on 2 values. Only 2 values. It's either 8 or 2. It's 2 if it's hydrogen. It's 8 for any other atom. Okay, so this column can only take on values of 2 or 8. And it's only 2 for hydrogen. If you have a hydrogen in your compound, then that value is 2. What does octet electron mean, OE? It means that in a perfect world, carbon wants 8. That's why you put 8 there. In a perfect world, fluorine wants 8. In a perfect world, nitrogen wants 8. Okay, it's obeying the octet rule. In a perfect world, hydrogen wants 2. That's why you only have 2 or 8. Okay, it's that simple. Don't make it harder than it is. Total valence electron, though, that's reality. That's what the periodic table gives you. Carbon has 4, and you know that if you look at the periodic table right here, you know that because carbon is right in that 4A family. So carbon has 4, so does silicon, so does uranium. Nitrogen has 5, Oxygen has 6. So does selenium, sulfur, and tellurium. Okay. It's given in the periodic table. That's why it's important to learn how to read the periodic table. And we're only worried about non-metals, because remember, non-metals are the ones that are going to be sharing electrons. We're not going to be looking at ionic compounds. So that's why we're not looking at the elements over here. We are looking at hydrogen, however, hydrogen, and then the rest of these non-metals. So keep that in mind in terms of determining the valence electrons. Okay, determining the valence electrons. So let me go back. And so let's fill this table. What we have is 1 carbon, it's got 8. 2 oxygen, 2 times 8 is 16. 1 carbon has 4 valence electrons. That would be in this column. Oxygen, each oxygen has 12. 2 times 12 is 12. Sorry, 2 times 6 is 12. Then you add them all up. 24. If this were a perfect world, you'd need 24 electrons to give each of the atoms in carbon dioxide an octet. 8 on carbon, 8 on oxygen, 8 on the other oxygen. Total of 24. Okay.
Excuse me, Professor.
Yes.
I have a question. It's where coming from?
The octet rule is based on, let's take a look at the periodic table. The elements that are most stable in the periodic table is the noble gases. Why? Because all the suborbitals are full. There is no empty suborbital. Neon's got 2 in the s orbital, 6 in the p orbital. Argon has 2 in the s orbital, 6 in the p orbital. Krypton has 2 in the s orbital, 10 in the d orbital, 6 in the p orbital. But the very last shell has 8. When you have 8 electrons in its very last shell, it has the same number of electrons as a noble gas. It gives it added stability. That's the octet rule. So that's why atoms, that's where 8 comes from. Okay, that's where 8 comes from. Now, in reality, we have 4 for carbon. But the magical thing about this table is this right here. If you take the octet electrons, 24, and just subtract the total valence electron, those are the electrons that you have to commit to bonds. 24 minus 16 is going to be 8. You have to commit 8 electrons in this compound for bonds. If you take 8 and divide it by 2, there are 4 bonds. There are 4 bonds. It just works out when you do this bond table. That's why I prefer bond table when it comes to complicated structure, because it always gives you that answer. It never fails, okay, except for the exception. And then the exception you just have to remember. Now, remember I told you that you use 8 electrons for bonding out of the 24, out of the 16. You've got 16 to work with. That's reality. But you now use 8 for bonding. If you subtract the 8 from the 16, those are the remaining electrons. That's this right here. And if you take the remaining electrons and divide it by 2, you now have the number of lone pairs for your entire structure. So the way you do this is you work with the connectivity. From the number of bonds, you just start from the central atom and start connecting the flanking atoms with the bonds, and you have to use up all 4. You can't put 3 on one and 1 on the other. It has to be evenly distributed. Okay, now we've used 8. We need to obey the octet rule. The carbon already has 8. It's got 2, 4, 6, 8. Carbon's happy, but this oxygen only has 4. So you need 4 more electrons right here. Now from our 4 lone pairs, we've used up 2. We put the other 2 right here. Okay, so if you follow this mechanical method of doing Lewis structure, you're never going to get wrong. Okay, so let me show you another one. This was sort of simplistic. Okay, but let me show you another one so that it makes sense. Let's take a look at this one right here. This is sulfur dioxide. Again, remember that sulfur dioxide has 1 sulfur. That's why I put it right here. And 2 oxygens. Comes from the formula. Then we put OE and TVE. OE can only be 8 or 2. There's no hydrogens here, so it's got to be 8. 1 times 8 and 2 times 8. That's a total of 16 plus 8, 24. But in reality, sulfur has 6 valence electrons right here. And oxygen has 6 valence electrons right here. And there's 2 oxygens, that's a total of 12. And you add 16, that's a total of 18. 24 minus 18. Okay, this is the connectivity right here. 24 minus 16 is 6. 6 divided by 2 is 3 bonds. This compound has 3 bonds. And the way you start it here is you have, this is the connectivity. You write one line to one oxygen, another line to another oxygen, but that's only 2 bonds. You need 3 bonds, so you just draw another line to another oxygen. It doesn't matter that it's skewed. That's okay, but you need to commit, you gotta have 3 bonds. From the bond table, it tells you, okay? It tells you how many bonds you have. Now, of the 18 electrons in our total valence electrons right here, we've used 6. 18 minus 6 is 12. That means that we have 12 remaining electrons that we haven't touched yet. 12 divided by 2, that's 6 lone pairs. 6 lone pairs. Okay, that's what we have right here. Remaining electrons, 12. 12 divided by 2, 6 lone pairs. So we take a look at the structure right here. This oxygen has 2. It needs 6 more. So we write 2, 4, 6. Remember, we have 6 lone pairs. Okay, so of our 6 lone pairs, we've already used up 3. We've got 3 more lone pairs to use up. This oxygen has 4 valence electrons. These 2 bonds right here represent 4. So it needs 4 more. So of our 3 lone pairs, we've now used up 2. This oxygen, the sulfur in the center, doesn't have 8 though. It only has 6 electrons around it. So you put the lone pair right there. You take care of the flanking atoms, the atoms in the periphery first, give everyone 8, including the bonds, and then you take care of the center. But it'll always work out. Now you can see that we do have 18 electrons here. 2, 4, 6, 8, 10, 12, 14, 16, 18. 18 total valence electrons. And 3 bonds and 6 lone pairs. The central atom has 1 lone pair. It's that easy if you understand the bond table. If you understand the bond table. Let's go to something more difficult. This one's charged. Okay, this one's charged. So we have to account for the fact that there's 1 extra electron in the structure. Chlorine, octet electron, total valence electron. Chlorine has 8. Oxygen, 4 times 8 is 32. Again, this column is always 8 or 2. 2 for hydrogen. A lot of students will make mistake by not remembering that. Okay, it's not difficult. It's either 8 or 2. Then we go to TVE, which is reality check. Chlorine has 7. You know that from its placement in the periodic table. Oxygen has 6. 4 times 6 is 24. And then the charge, this charge right here, means that there's 1 more extra electrons in total valence electrons. If this was a positive, then you need to subtract 1. If it's negative, then you add 1. If it's -2, you add 2. The negative tells you there's an extra electron in that structure. The positive would tell you you're missing 1 electron in that structure. But this is negative. So instead of 31, we write 32. 40 minus 32 is 8. 8 divided by 2, there are 4 bonds. 4 bonds in this structure. You don't even have to write the structure. You already know that there are 4 bonds. If I subtract 8 from 32, that's 24. 24 divided by 2, 12 lone pairs. Even without the structure, I know the number of lone pairs. 12 lone pairs, 4 bonds. Let's see if that's true. Here's my connectivity. Chlorine's in the center. When you have a formula, usually the first atom is the central atom, except when it's hydrogen or fluorine. Hydrogen and fluorine can never be central. but chlorine is the central atom here, and then the oxygen surrounds it. So this is what we start with right here. And then we have 4 lines, 1, 2, 3, 4. That's your 4 bonds. And then what you will see is that each oxygen already has 2 from that shared electrons. It needs 6 more. 6 here, 6 here, 6 here, 6 here. 6 times 4, 24. That's exactly the number of electrons we had remaining here. 24 divided by 2, 12 lone pairs. So let's see how that works out. 4 bonds, 24 remaining electrons. That's 12 lone pairs. 3 apiece on each oxygen. That's a total of 3 times 4. That's 12 lone pairs. Okay. So that's your Lewis structure. You need the Lewis structure if you want to determine molecular geometry. And we'll do that shortly. Here's another example, PO3 minus 3. The minus 3 means that you have 3 extra electrons in the total valence electrons. You do this enough times, it becomes automatic. Okay, so we know that phosphorus is 8, oxygen is 3 times 8, that's 24. In reality, phosphorus has 5, same as nitrogen. Oxygen has 6, 3 times 6 is 18. And then the charge of phosphite is minus 3. So you have to add it here. You have to. This is 32. This is 26. 32 minus 26, that's 6 divided by 2. You've got 3 bonds in this structure. Without even drawing anything, you already know there's 3 bonds. Again, the beauty of the bond table. If you subtract 6, because remember, you're committing 32 minus 26 is 6. You're committing 6 electrons to bonding. So if you subtract 26 from 6, there's 20 remaining electrons. 20 divided by 2, that's 10 lone pairs. So without doing any structural work, I know this compound has 3 bonds and 10 lone pairs. Let's put it together. Here's 3 bonds right there. And then you can see that each oxygen needs 6 electrons to get an octet. That would be 9, but this phosphorus is lacking an octet. Guess what? That phosphorus will get the last lone pair. There are 10 lone pairs in this structure. 3 in the oxygen, 3 in the oxygen, 3 in the oxygen, that's 9. And then that phosphorus has 1 more 10. Okay. Let's take a look at this complicated compound. Okay. Again, I want to illustrate to you, it's easy if you use the bond table. If you try to do electron gymnastic, where you say phosphorus brings in 5, hydrogen brings in 1, oxygen brings in 6 apiece, and then you try and work out how to arrange it so that each atom has an octet, you're going to get crazy because it's too hard. The bond table gives you a starting point of how to connect it. Okay, it tells you the number of bonds, it tells you the number of lone pairs, and all you have to do is make sure you obey the Octet rule. So this is dihydrogen phosphite, 2 hydrogen, and PO3 is phosphite, and it's got a negative charge. So we do our multiplication table again, 1 phosphorus, 3 oxygen, 2 hydrogens this time, and then there's a charge. So this column, OE, can always be 2 or 8. 2 or 8, write that down somewhere because you're going to forget. Phosphorus, it's 8. Oxygen, it's 8 times 3, that's 24. And then hydrogen, it's not 1, it's 2. 2 times 2 is 4. If you're going to make a mistake in this bond table, you're going to do it here, okay? I've seen so many papers where that's where the mistakes come from. You're going to do it here. You're going to have a brain lapse and you're going to forget. Now let's take a look at total valence electrons. Phosphorus has 5, oxygen has 6, hydrogen has 1. So let's put 5 times 1 is 5, 3 times 6 is 18, 2 times 1 is 2, and then there's a charge here, 1. So if you add that all up, that's 26. 36 minus 26, that's 10. that you need to commit 10 electrons to bonds. That means 10 divided by 2, there are 5 bonds in this structure. So this is the connectivity. Okay, you don't know that, so I would have given it to you. And all you do when you write 4 bonds is just connect the atoms that are adjacent to each other. You're going to have a line here, 1, a line here, 2, a line here, 3, a line between the oxygen and hydrogen, that's 4, and the line between the oxygen and hydrogen here, that's 5. That's your 5 bonds. So again, 5 bonds. What you guys are going to do now is subtract 10 from 26. Why 10? Because the 5 bonds make up your 10 electrons. And you've already used 10 electrons in this structure right here. So from the 26, you have to subtract 10. That leaves 16. 16 divided by 2. This guy has 8 lone pairs. Okay, 16 divided by 2, 8 lone pairs. Without writing the structure, I know it's got to have 8 lone pairs. If you didn't have the bond table, you'd really be scratching your head because you don't know in what directions to go. The bond table gives you direction. Okay, so we can put 8 by putting 6 right here because this oxygen only has 2. This oxygen has 4, so we can put 4 right here. So 3 plus 2 is 5. Remember, we need 8 lone pairs. This oxygen needs 2. And then this phosphorus picks up the last one. That would be 8 total. And so your structure would look like that. Okay. The bond table, it's the way to go. That's why I teach it this way. Rather than chance and do it trial and error by trying to figure out the structure, the bond table gives you direction in doing the Lewis structure. Yeah, it takes a little bit more time in the beginning because you have to make this table, but that table gives you all the answers. Okay, that table gives you the answers. Here are other exercise. This, when you do this enough time, you will know there are 4 bonds in this structure, and these guys will have 3 lone pairs apiece. Okay, this silicon dioxide, same as carbon dioxide. You don't have to redo anything. Carbon dioxide is linear. It's got 4 bonds between these 2 oxygen, this oxygen and silicon, this silicon and oxygen. And then there's 2 lone pairs on each oxygen. Okay, so here are the Lewis structure for these. If you can do the Lewis structure, the last part, the molecular geometry is such a breeze. It's such a breeze, but you need the Lewis structure. Now, before I do the molecular geometry, let me show you some exceptions to the Octet Rule. Okay, remember the Octet Rule simply means that the atoms want 8 electrons in its valence shell, and it has 8 by sharing. So like this silicon right here, 2, 4, 6, 8 through the bonds. This oxygen, 2, 4, 6, 8. The Octet Rule, except for the hydrogen. Hydrogen wants duet rule. Right here, it's certainly happy with 2 electrons. In fact, it can only take 2 electrons. It's called the duet rule. So what are the exceptions? When you have an odd number of electrons. If I tell you, show me the Lewis structure of NO, or if I ask you, does the NO molecule, neutral, not minus, not plus, NO molecule obey the Octet Rule? No, because carbon comes in with 5, oxygen comes in with 6. That's an odd number of electrons. 5 plus 6 is odd. Odd number of electrons can never obey the Octet Rule. Can never. Okay. If this were NO plus, it would obey the Octet Rule, because now NO plus means that of our 11 electrons from NO, we take away 1 more because it's plus. It now has 10. It's even. It would obey the Octet Rule. If it's NO minus, it means 1 more electron. We got 11 originally from NO. The minus makes it 12. 12 is an even number. It would obey the Octet Rule. Okay. But if you count and the chemical has an odd number of electrons based on the charge overall, it's not going to obey the octet rule. Try as you may, it will never obey the octet rule. And then there's electron deficient. I told you about boron. It's got 3 in its valence shell. It's totally happy with 6. Okay. And beryllium hydride as well. And then some elements actually use their d orbitals. So let me break out. Elements here in the periodic table, you see, once you get into the 3rd period, this is the 3rd period. How do you know it's the 3rd period? It's got 3 right there. But remember, the d orbitals start showing up on the 3rd shell. So any element below in the 3rd period and lower, 3rd period, 4th period, 5th period, can actually use their d orbitals. And we have something called valence shell expansion. You could have more than 8, which is a lot of chemicals, I know. But you guys aren't taking chemistry 200, okay? So you don't have to worry about that. In chemistry 200, you would. That's general chemistry. Here, we generally obey just the octet rule because the molecules in life are generally on the in the 2nd period right here. So those are some of the exceptions, okay? Now, let's jump into molecular geometry. Okay, molecular geometry is super easy, but the key in molecular geometry is you got to be able to read and use this table, okay? If you know how to use this table, you will always get the electronic geometry and the molecular geometry correct. And this is the extent for this class. In general chemistry, there's 2 more rows that you have to worry about. You guys don't have to worry about that, okay? So I'm going to close this, and then because we're pretty much done here, and I'll show you how we do molecular geometry. Okay, do you guys have any questions on that? I hope it's clear. This is recorded so that you guys can see exactly how easy it is to do the Lewis structure based on the bond table. The molecular geometry is even more simple, okay? And the reason why we want to know molecular geometry is because the shapes of the chemicals is the function, okay? The shape of the chemical gives it the function. So a lot of times we detect chemicals through our sense of smell. Something can be pleasant, like smelling a rose, or maybe someone's barbecuing in the back. You get you salivating because it triggers some memory, or it could be really awful, like cadavers or something really rotten. And that's because the molecules get airborne, and these molecules, they go into our orifice in our nose, and then it triggers a response. But it's the shape that triggers a response.
The detection of specific airborne molecules, referred to as autogens, results in the sense of smell. As the autogen is inhaled, it moves through the nostril and into the nasal cavity. There it comes in contact with the olfactory epithelium. The olfactory bulb, which lies above the nasal cavity, receives sensory information from the olfactory epithelium. Within the upper nasal cavity, the autogens dissolve in the mucus lining, where they can interact with receptors on cells in a specialized region on the olfactory epithelium.
So the shape of the chemical will trigger a response, and then that response will either be pleasant or offensive, okay? So it's really important to understand shape. Here's a chemical right here on the left, okay? That's a primary structure for chemicals that are addicting. Look at the shape. It looks like one compound, but that's codeine, okay? You put codeine in your cough medicine so that it doesn't hurt. This is morphine. You take morphine when you're really hurt because it numbs the pain. And this is heroin. The story with heroin was that the chemists simply took these OH group on morphine and did some chemistry to it, and they made this chemical. It's called methoxy. these OCH3 groups are called methoxy. So they derivatized morphine and made it methoxy. And the idea was that we could make a chemical that is like morphine. You need less to numb the pain. That was the original idea of the synthesis of heroin. Okay, you could take less for the same amount of morphine, and it numbs the pain as well. They didn't know it was addicting. Okay, they didn't know it was addicting, and it was one of the worst mistakes. Someone would have eventually discovered it. But look at the skeleton behind all of this. This right here is methamphetamine. Okay, so hydrocodone, oxycodone, they all have that skeleton. And again, it's because of the shape that triggers a chemical response in our body. And so that's why understanding molecular shape is important. And even though you guys are not going to know molecular shape at this level, you guys will be able to predict the molecular shape around each atom after our discussion today. Okay, so this is just how codeine receptors work, and we can talk about that. But I want to get into this because I don't want to dwell too long on that other part that you guys can read on, because we do have limited amount of time. So VSEPR means valence shell. So those are the electrons in the outermost. Electron pair, those are the lone pairs or the electrons that are involved in bonding. Repulsion. Electrons are negatively charged. And so you put any pairs of electrons. Electrons will exist in pair in an orbital. That's okay. They can be close together because they have opposite spins. But you take one pair of electrons and you put it near another pair of electrons, they're going to repel because negative and negative don't like each other. So that's what this theory is based on. It means that the valence electron in an atom want to stay as far apart as possible, and they'll take on a geometry that allows them to do that. Okay, so these are just the driving force of all of that. You can read it on your own. The idea is that when you have two lone pairs or two regions of electron density, the furthest apart they can be is 180. And 180 is a linear geometry. When you have three regions of electron density like this, then the furthest apart they will be geometry-wise is trigonoplanar. When you have four regions of electron density around a central atom, then the furthest they can be is 109.5, or a shape of tetrahedral. Don't worry about these last two, okay? Don't worry about these last two because we're not going there. You guys are not in chemistry 200, so don't worry about that, okay? Just see. So let's take a look at this movie, if you guys, and then I'll show you how to use, how easy it is.
The electron pairs that surround a central atom are most likely to be found in confined regions of space called electron domains. The arrangements of the electron domains about a central atom are determined by the electrostatic repulsions between like charges. The electron domains stay as far apart from one another as possible, while at the same time, they are held by their attraction for the central atom. When there are two electron domains about a central atom, they are located 180 degrees apart to minimize repulsions. Three electron domains about the central atom take up positions in a plane, separated by 120 degrees. Four electron domains form a tetrahedral arrangement about the central atom.
So that's as far as we're going to go. Some book calls it regions of electron density. Some book calls it domain, but it's basically electrons that are pointing in space somewhere. Okay, so these are the rules. Don't worry too much about the rules. You guys can read them on your own. But the idea here is the following: when you have a central atom, the central atom is going to be an atom that has two or more bonds. So when you think about a molecule, think of a bicycle wheel where the central atom is at the center and the peripheral atoms are the rim. okay, like in this particular case. And if there's a bond between the central atom and another atom, then we call that one domain, one region of electron density, okay? This right here would be two bonds to another atom. That would be two domains. Two domains, if you had this and this. An electron pair is a single domain. You count that as a third region of electron density. If you have multiple bonds like that, that's still considered one domain because it's pointing in one direction, pointing at one direction. Even if you have a triple bond, it's pointing in one direction, it's pointing to one atom. So this particular picture that you see here, that's a central atom with three domains around it. The bonds to an atom is one domain. Multiple bonds to the same atom is one domain. Depending on how many atoms it's connected to, you can count that as a domain or regions of electron density. And then lone pairs of electrons count as its own domain. Okay, lone pairs of electrons count as its own domain or regions of electron density. So if you know how to count domains or regions of electron density, then all you have to do is go to this table, because these right here will tell you, you can either have 2, 3, or 4 regions of electron density or domain. If you have 2, then the electronic geometry is going to be linear, no doubt about it. If you have 3, then the electronic geometry is trigonal, no doubt about it. If you've got 4, the electronic geometry is tetrahedral. You don't have to think about it, it's there. Now, what you need to do next is look at those domains. Think of it as spokes on a wheel, spokes on a wheel. We have 3 spokes here, 3 domains, okay? But look at the ends of the spokes of the wheel. If they have bonded atoms, then those are bonds. But if they have lone pairs, those are non-bonding. So you go over here, how many bonded atoms at the end of these domains? 2, no lone pairs. The molecular geometry is linear. Here, you could either have all 3 at the end of these domains connected to an atom, in which you have 3 bonded atoms, no lone pairs. The geometry would be trigonal planar. If you have 2 of these 3 domains with bonded atom and 1 lone pair, just like this one, then the molecular geometry only accounts for the atom. Only accounts for the atom. Yeah, the lone pairs make it crooked because it's there, but the geometry is based on the atom. That would be bent, and it would be called bent trigonal. This would be bent trigonal. Okay, so that's how you use this table. If there are 4 domains, then at the end of each of these domains could be bonded atoms, in which case it's tetrahedral. If you have 4 domains and 3 of these are bonded atom and 1 is lone pair, then you have a pyramidal type of shape. And if you have 4 domains and only 2 of them at the ends have bonded atoms and 2 lone pairs, then it would be bent tetrahedral. You use this table to give you an idea of the bond angle, the molecular geometry, the classification AB2, E2, AB4, and the electronic geometry. This table will give you the answer, but it comes from the Lewis structure. Comes from the Lewis structure. So let me just illustrate here in this next example, and you guys can easily figure it out. Look at this right here. Sorry. Look at this right here. This is ammonia. How many domains does that have? You can count 1, 2, 3, 4 domains. Okay, just practice counting domains. This is carbon dioxide. How many domains is that? Always pay attention to the central atom. It's the central atom that dictates the geometry. Okay, that has 2 domains. Albeit this is a multiple bond, but it's pointing in one direction. So that's one domain. This is a second domain right there. 2 domains. This right here, this carbon central, it's got 3 domains or 3 regions of electron density. This chemical right here, water, it's got 1, 2, 3, 4, because a lone pair counts as a single domain. So this chemical right here has 4 domains. This chemical right here, this is ozone. Look at the central atom, oxygen. It's got 1, 2, 3 domains. Look at, this is on our exception, BH3. It's only got 6 valence electrons, but look, it's got 3 domains. This NO2, it's got 1, 2, 3 domains. So now we can figure out what the geometry is for each one of these, just based on this guy right here, just based on that guy right there. We can come up with the geometry for all of this. And that's essentially what we have right here. We got 4 domains on NH3. So we go over here under 4 domains. You need to figure out the domains from the Lewis structure. And of those 4 domains, 3 of them are bonded atoms. So we're here and 1 lone pair. That geometry is pyramidal. That's a pyramidal geometry. It's classified as AB3E, 3 bonded atoms, 1 lone pair. Its electronic geometry is tetrahedral. Let's take a look at ozone right here. It's got 3 domains, but 2 of them are bonded atom, 1 of them are lone pair. So we go over here to 3 domains right here. 2 of them are bonded atom, 1 of them is lone pair. It's a bent trigonal. It's a bent trigonal. It's that easy, really. Okay, I just save you like 5 hours trying to figure this out. Let's take a look at this guy. Yes.
So for the bent trigonal, the lone pairs,
right
does
here.
it have to be, in order to be bent, does it have to be on that central atom, or can it be in any domain?
No, it has to be, you have to count the domain on the central atom, because it's the central atom that is the anchor. It's the hub on the wheel. Okay, so if you've got multiple central atoms, then you determine the geometry around each of the atoms that have more than 2 atoms bonded to it. And I'll show you an example of that. Okay, but you need to determine the geometry around each central atom first. This one, 3 domains, so you just follow this. And I'll show you an example where you have multiple central atoms, and then you have to determine the geometry around each central atom. Okay, but it's the same analysis. It's the same analysis. So I think we're good here, okay? I think we're good here. This carbon has 3 domains and no lone pairs. You go over here, 3 domains, no lone pairs. That's trigonal planar around that carbon. Okay, so let's go to something more sophisticated. Okay, let's do this. Now, these are just examples. Again, here, BH3, 3 domains. It's going to be right here. Trigonal NO2 minus. That's 3 domains, 1, 2, 3. Here's how I show you that, the 3 domains. So again, 3 domains, but 2 of them are bonded atoms, 1 of them are lone pair. That's a bent trigonal. Okay, so these are all the examples of the different molecular geometry. But you need to look at the central atom and figure out how many domains come out of it, or how many regions of electron density. Once you understand that, then it's a snap. You guys will be able to easily get the molecular geometry. Okay, now let's do this. That's an interesting compound. Okay, this is a compound with multiple central atoms, but take a look. In organic chemistry, what you guys will learn is that whenever there's a bent, like right here, you know, chemists are very lazy. We're very lazy. So rather than writing carbon here, we leave it as a bent line, and we understand that that's a carbon, that's a carbon, that's a carbon, that's a carbon. So whenever there's a bent in the structure, we know it's a carbon. That's just the nomenclature that we have. So this is a carbon, 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 and then carbon always has 4 bonds. Carbon always has 4 bonds. So you see this carbon right here? That's a carbon, and it's got 1, 2, 3. Usually I don't put this hydrogen in there, okay? But you would know that if that carbon only showed 3 bonds, then the fourth one goes to a hydrogen. We leave it out. But let's figure out what is the molecular geometry around each of these central atoms. Here's the carbon right here. This carbon has 3 hydrogens. That means there's 1, 2, 3, 4 domains, because those 3 hydrogens are actually individual bonds. If it's got 4 domains around this carbon, no lone pairs, that's tetrahedral. That's tetrahedral. OCH3 groups are tetrahedral. Tetrahedral, tetrahedral, tetrahedral. Let's take a look at this nitrogen. This nitrogen has 1, 2, 3, 4 domains, but one of them is a lone pair. One of them is a lone pair. So 4 domains, 1 lone pair. So we're here, 3 bonded atoms, 1 lone pair. Where are the bonded atoms, you might say? See this nitrogen? It's got a bonded atom to this carbon, because remember I told you wherever there's a bent shape, it's a carbon. This is a carbon, that's another carbon. So this nitrogen is bonded to 3 carbons and 1 lone pair. What's the geometry around that nitrogen? The geometry around that nitrogen is pyramidal. Pyramidal. Because it's got 4 domains, 3 bonded atom, 1 lone pair. Let's take a look at this nitrogen as well. 1, 2, 3, 4. 4 domains. One of them is a lone pair. It's also pyramidal. Let's take a look at this carbon right here. This is a carbon because again, it's in the intersection of bonds coming in. And so it's implied that's carbon. You guys will learn this in organic chemistry. It's implied that's a carbon right there. Look, let's count the number of domains. 1, 2, 3. This carbon has 4 bonds. 1, 2, 3, 4. So that's okay. And there are 3 domains. That carbon right there would be, it's got 3 domains, 3 bonded atoms. That would be a trigonal around that carbon. It's you don't have to work that hard if you can count domains. Let's try one more. Let's try this oxygen. No, you can't count that oxygen as a geometry. Why? It's at the end. It doesn't have a geometry. Okay, any terminal atom is not going to dictate a geometry. It's just dangling out there. So you don't want to say that this has a linear geometry or anything. It has no geometry. It's dangling. But around this carbon right here, that would be trigonal planar. 1, 2, 3 domains. Around this nitrogen, 1, 2, 3, 4, that would be pyramid. Around this carbon, 1, 2, 3, that would be trigonal. You just have to count the domains and then learn how to use this table. Learn how to use that table because it'll be pretty simplistic once you do that. So here are all the tetrahedral. I told you all these methanes are tetrahedral. All these carbons over here are trigonal. And then these are pyramidal with the lone pairs. This chemical, by the way, is caffeine. So that's an example where you have a molecule, very sophisticated molecule, more sophisticated than what we were working with. And it has multiple geometry. And for each central atom, you have to dictate what the geometry is around that. And then when you put it all together, it looks like this. It looks like that. Okay, so hopefully I've answered your question in terms of how to determine the geometry if you got more than one central atom. If you have more than one central atom, and these are examples of that. These are examples of the sophisticated structure these chemicals have because each central atom in that compound has a geometry around it. You can tell right here, this carbon right here, it's got 1, 2, 3 bonds. That's a carbon right there. The 4th one has got to be a hydrogen. So even though it's not drawn here, you guys will learn that when there's only 3 bonds on the carbon, the 4th one is implied and it's to a hydrogen. That's just known, especially if you're going to go into organic chemistry. So that means that this has 1, 2, 3 domains, 4 bonds, 3 domains. That's trigonal, planar around that carbon. Trigonal plane around that carbon. Let's take a look at this carbon right here. Remember I told you the intersections of lines is a carbon. This has 1, 2, 3 but it's only got 3 bonds. That means that the 4th bond that you don't see is to a hydrogen. It's got 4 domains, in other words. 4 domains, no lone pair, tetrahedral around that carbon. And that carbon right there is actually right here. That's the this carbon is this carbon right here. This carbon right here is this carbon. It's tetrahedral. It's tetrahedral. Okay. So that's how you determine molecular geometry. Okay. It took longer than I want, probably about 15-20 minutes, but learn how to use this table. Learn how to use this table. Now, let me go ahead and talk to you guys about polarity, because that's the last thing I want you guys to learn is polarity. And polarity is built from molecular geometry. It's built from molecular geometry. So everything's a building block based on the previous lesson that we just learned. Okay, so we're going to be looking at polarity right here. The idea of polarity is that, remember, it's the electrons that ties the atoms together. It's the electrons that ties the atoms together. But sometimes the electrons are going to be distorted to one side. And remember, electrons are negatively charged. So if it's distorted to one side, like in this picture right here, then the side that has the greater amount of electrons is more negative, and the side which have the least number of electrons is more positive. So it looks like a magnet, a north pole and a south pole. Okay. And that's where polarity originates from. Like planet Earth, it's got a north pole and a south pole. It's got, you know, the ends are north and south. A magnet has a north pole and a south pole. Molecules can have poles as well. One side, we don't say north and south, we say partially positive, partially negative. The area where the electrons tend to reside in more greatly is the negative part, and we use this Greek symbol delta to indicate there's a partial negative charge in this region and a partial positive charge in this region. So we say that these chemicals, because they have a separation of charges, are polar, just like magnets are polar. That's what it means. When you have a chemical like this, where the electron cloud is evenly distributed around the entire molecule, so there's no distortion on the electron cloud, we say it's nonpolar. We say it's nonpolar. Okay, so you first need to understand what makes things polar or nonpolar. When you have a bent pyramid or bent, whenever you have a lone pair in the central atom, it's automatically polar because it distorts the geometry. When the geometry of a molecule is not symmetric, it's going to be polar. If the geometry of a molecule is symmetric, it's going to be nonpolar because the electrons are going to be evenly distributed around the entire molecule. Okay, so again, an illustration here. Think of it as a tug-of-war game. When you have 2 atoms tugging on electrons and one is stronger than the other, then the electron is going to be drawn towards that side, and we say there's a winner in that tug-of-war game. It's a polar situation. But when it's even, like in this particular case, because they have the leverage and they all have equal strength, then it's nonpolar. But as soon as you break that leverage like this is bent, then that becomes polar. So that's why you need to know the molecular shape, because you need to see whether there's a distortion on the shape or the shape is even throughout. That's why you need the molecular geometry. Now, this just talks about oxygen or water, and the fact that water is a very polar chemical. What makes a chemical polar? When it has a stinginess. It wants to hoard electrons, and the elements that wants to hoard electrons the most are these elements right here in the top right corner. We measure their stinginess for electrons in terms of something called electronegativity. So the elements on the far right are the most electronegative. Fluorine is 4, oxygen is 3.5, nitrogen is 3.0, chlorine is 3.0. Those are the most stingiest elements for electrons. Okay, and so whenever an atom bonds to them, and it's not symmetric, the electrons tend to reside on these stingy atoms: nitrogen, oxygen, fluorine, and chlorine. NOF. I like to say NOF and chlorine. Okay, so when you have chemicals like this, CO, is that a polar or non-polar? Well, you know that the electronegativity, let me just show you this. You know that the electronegativity of the element based on the periodic table is greatest on fluorine and the lowest for fluorine. So the further closer you are to fluorine, the more electronegative your element is. If two elements are separated in the periodic table, that means that their electronegativity is going to be very different from each other. But if they're next to each other, their electronegativity are very close to each other. Still different, but close. When we have CO, CO is this chemical and that chemical. There's going to be a difference in electronegativity. That's going to be a polar chemical. NO is not so polar, but still polar. N2 is non-polar because you've got two elements that are the same. So to determine for chemicals in which there's only two atoms, whether it's polar or non-polar, just look at the atoms and measure its electronegativity. If the electronegativity difference, what is the difference? Let me show you that over here. If I have carbon and oxygen, carbon's 3.5, carbon is 2.5. So the difference is 1. 3.5 minus 2.5 is 1. That tells you the measure of how the electron cloud is distorted. If you have oxygen and nitrogen, oxygen's 3.5, nitrogen's 3.0. The difference is 0.5. It's still polar, but not as much as CO. In fact, you don't even need these numbers. All you need to do is look at the distance, the separation between two atoms. A chemical like SO is less polar than a chemical like TEO. Why? Because their difference in electronegativity is going to be bigger for TEO than SO, because SO are closer together, which means that they have closer electronegativity. Tellurium is way down here. Its electronegativity is going to be much more different than oxygen. In fact, you can see that this is 2.1, that's 3.5. This is 2.5, that's 3.5. The difference is much bigger between tellurium and than sulfur is. Okay, so that's the first thing that you would need to do in order to figure out whether a chemical is polar or non-polar. For binary, look at the difference in electronegativity. Okay, the difference in electronegativity, and that's what you see right here. Right here. Right here. When the difference in electronegativity is between 0 and 0.4, then it's somewhat covalent. When the difference in electronegativity is 0.4 to 2.0, then we say it's polar covalent. Still sharing, but not equally. And then when it's greater than 2.0, then that's anionic. The electrons are actually transferred. So for two atoms that are connected, you just need to look at the electronegativity to determine whether it's polar covalent, covalent, polar covalent, or ionic. Okay. Let me continue here because I really want to talk to you guys about this. Let's take a look at this right here. These are binary compounds. And the question is, that's the difference in electronegativity. Those are pure covalent. That has an electronegativity of about 0.4. And so you just have to look at the difference in electronegativity, and then you can figure out whether or not the chemical is polar covalent, covalent, or ionic. And these guys tend to be more ionic here. Okay, so for binary compounds, you just have to figure out what the electronegativity difference are. Okay, but let's take a look at these chemicals over here. Which of these are polar and which of these are non-polar? See the silicon? They have same terminal atoms throughout. That's a non-polar chemical because it's symmetric. See this chemical here? Well, this carbon, the entire molecule is symmetric. Okay, it's got two carbon in the center and 2 bromines at the end. That's a non-polar chemical. Even though the bonds are polar, the entire molecule is non-polar. This is a polar chemical because it's not symmetric. This is a non-polar chemical. This is a non-polar, this is a polar chemical. This is a polar chemical because of the bent and the fact that the oxygen has lone pairs. So you can use this scheme to determine whether a chemical is polar or non-polar. Okay, how many central atoms? If there's only 2 central atoms, then you look at the difference of electronegativity. If there's a binary compound, 2 atoms in the compound, you look at the difference in electronegativity. But if it's any one of these, you look at whether it has 1 central atom. And what you need to do is, does the central atom have lone pairs? Yes, it's polar right away. Are the terminal atoms different? It's polar. Okay, so whenever the symmetry is broken, it automatically becomes polar. Let's say we have more than 1 central atom. So we have more than 1 central atom. Well, if we have more than 1 central atom, then we look at the terminal atoms. We look at the terminal atoms and we see whether or not they're different. If they are different, it's polar. If they're the same, like here, it's non-polar. Okay, so all these right here are polar. All the ones in blue are non-polar. Okay, so you have to know the geometry. And why is that important? Why is that important? Because the last thing I want to show you is intermolecular forces. And the intermolecular forces, and that's the last thing I'll definitely talk to you guys about. The type of intermolecular forces that you guys are going to be seeing in this class, and I'll just shoot straight to the different types, are these right here. Okay, you guys are going to see dipole, this one right here. And dipole arise because 2 molecules are like magnets. And so they line themselves up like magnets because they're polar. Okay, so if you have polar chemicals in your mixture, or you're dealing with polar chemicals, it automatically has dipole interaction. All atoms have what we call London dispersion force. Why? Because all atoms have electrons. All atoms have electrons. What exactly is London dispersion force? London dispersion force is a type of force that arise. Let me see. That's dipole. Here's London dispersion force. What happens is that nonpolar chemicals, even noble gases, will have electrons. Every once in a while, especially at low temperature, the electrons bunch up to one side. Like you see right here. You see right here, the electrons bunch up to one side. And when it bunch up to one side, especially at low temperatures, then that side of this nonpolar chemical has partial negative. The neighbor next to it is going to have its electron repelled from that side. So this side's partially negative, this side's partially negative. The electrons are going to go to the opposite because electrons repel. And so this side becomes partially positive by the mere fact of its neighbor having its electron move to the other side. Now that partial negative and that partial positive are attracted. That's called London dispersion force. And this thing trickles down. It's like the wave in a sporting event. You remember when the Padres play and everyone starts the wave? Well, once this thing occurs where there's electron being distorted to one side, even though they're nonpolar, then these things are going to have a chain reaction. And then that's what makes these things stick together. Okay. So the 3 forces that you guys are going to be looking at is London dispersion force. All chemicals have London dispersion force. Dipole, only polar chemicals have dipole, and hydrogen bonding. Hydrogen bonding occurs when hydrogen is bonded to those electronegative elements that I talked to you about because of something called special interaction due to hydrogen bonding occurs because of the fact that the hydrogen is one proton, one electron. When that electron's being stolen by those electronegative element, that proton's naked. That hydrogen, the proton and the hydrogen's naked, and it makes it have a special type of intermolecular force called hydrogen bonding. So what question you will see is the following. Of these chemicals, which of these have London dispersion force? Which of these have dipole-dipole? Which of these have hydrogen bonding? And which of these are polar? Are these polar or non-polar chemicals? And so let me walk you through this, and I'll end with that. This is C2H6. This is what we call a hydrocarbon. It's got 2 carbons in the center and then 3 hydrogens apiece attached to the carbon. It's basically a chemical that's totally symmetric. Totally symmetric, okay? If it's totally symmetric, it's not going to be polar. And it doesn't have hydrogen bonded directly to an electronegative element. So the only force this chemical has is London dispersion force because it has electrons. And we say that this chemical is nonpolar. This chemical is nonpolar. So we can say that, at least for this, it's got London dispersion force and it's nonpolar. Let's take a look at this guy. This guy, by the mere fact that it's got a carbon in the center again, 3 hydrogens are attached to the carbon, and then an oxygen and an OH. That's methanol right here. This is methanol. The fact that the molecule is distorted means it's polar. The fact that there's hydrogen bonded to oxygen, an electronegative element, tells you it's got hydrogen bonding. The fact that it has electrons tell you it's got London dispersion force. So this chemical has all 3. This chemical has all 3, and it's polar. Let me share with you one more trick. Whenever a chemical has hydrogen bonding, it's also polar, and all molecules have London dispersion force, all molecules. If it's got hydrogen bonding or it's got dipole-dipole, it's going to be polar, okay? So when you check mark these 2 boxes, you better put P right there. Let's take a look at this. This is not so different from methanol, except now one of the hydrogens replaced by fluorine. But fluorine is not attached to the hydrogen, it's attached to the carbon. So this chemical is certainly polar, but it doesn't have hydrogen bonding. The forces that this chemical have is London dispersion force, dipole-dipole, no hydrogen bonding, and it's certainly polar, okay? This chemical's got oxygen right in the center, so it's symmetric. And the hydrogens are not attached to the oxygen. So this chemical is nonpolar because it's totally symmetric. And the only force that this chemical has is, well, actually, this chemical has a pair of electrons here. So it's going to be bent. So it is polar, okay? And it's got dipole-dipole. This is nitrogen bonded to hydrogen. It's got hydrogen bonding involved. Once you got hydrogen bonding, it's polar. It's got London dispersion force. And of course, it's polar right there, okay? Because it has hydrogen bonding involved. And then this chemical right here, it's not symmetric. So it's got dipole-dipole. It's got electrons because it's got atoms, but there are no hydrogens involved. So it doesn't have hydrogen bonding. So it's polar, dipole-dipole, London dispersion force. Okay, so through this example, everything comes together from what we just talked about. From this example, you are able to determine whether it's polar or nonpolar. Polar or nonpolar comes from the molecular geometry. If the molecule is totally symmetric throughout, then it's nonpolar. If it's not symmetric because one of the end atoms is different or one of the central atoms have lone pairs, then it's going to be polar. And you know the molecular geometry because you can work out the Lewis structure and then use the VSEPR table. But that basically is what this chapter is about. It brings everything together in terms of its molecular shape, and the rest of these notes just kind of give you examples of these things that we've talked about. Okay. Make sure that before this quiz that you guys are scheduled to do this weekend, make sure you know how to name compounds. That would be, if you guys are taking the lab, try and complete the nomenclature activity, and also try and start the next activity, activity number 3, I believe. Okay, the activity number 3 gives you training on molecular geometry. That way you can practice these things. And then the last thing I want to mention is, please do take a look, download this supplement information, because that's where you're going to find that VSEPR table, and then go to the website and look at the sample tests. You want to take a look at these questions right here: atomic theory, nuclear chemistry, and then right here, molecular geometry. It gives you many different types of questions in terms of what we just talked about. What is the VSEPR molecular geometry of O3? You guys don't have to do that because we already did it in our exercise. O3 has an oxygen in the center, another oxygen in the 2 sides. It's got 2 bonds to one side, 1 bond to the other, and it's got a lone pair in the central oxygen. So it's 3 domains, but 2 of them are bonded atoms. So it's bent trigonal. You would say this one right there. Okay. And if you look at the key, you will see that that's the correct answer as well. So these will give you a bunch of practice on the type of questions that we just covered. Also know your ions. If you look at this right here, go to this right here. Because if you click on that, here are all your polyatomic ions. Remember that a chemical that like this, HCO3, yeah, this is called hydrogen carbonate, but it's also known as bicarbonate. Okay, whenever you have a polyatomic ion, CO3 is carbonate. It's this chemical right here, carbonate. But when you put a hydrogen in front of that, so now it goes from -2 to -1. It's not only called hydrogen carbonate, but more commonly it's known as bicarbonate. I don't know why they do that, but whenever you put a hydrogen in front of a polyatomic ion and it's still charged, now that is called a whatever that is. This chemical right here, phosphate, if you put a hydrogen in front of that, that's called biphosphate. This chemical right here is not only hydrogen phosphate, it's also known as biphosphate. That's the common name that is out there. And you guys will see that in some of my questions. I told you in this discussion what I wanted you to discover by doing that, okay? That you don't have to memorize these things. If you know the pattern, then the geometry is going to be the same based on the valence electron. CO2 has the same geometry as SiO2, has the same geometry as CSeO2. Why? Because the central atom has 4 valence electrons and the flanking atoms have 6 valence electrons. Doesn't matter what the elements are, they have the same, so they're going to have the same geometry as CO2. H2O, likewise. You have H2O or H2SE or H2S, all the same geometry. Why? Because they all have the same number of valence electrons. That's what I wanted you guys to realize. And that way you don't have to memorize all those structures. You just have to memorize the main ones and then draw from that. So that's, if you have any questions.
Yes, Professor.
Yes.
Group activity is for chemistry lab?
The activity that I showed you is this one right here. The group work that I had is this one right here. This is for lecture. And remember, I assign you guys group to do. Some of you work solo, that's fine, but it's basically this one right here. Just find that real quick in the announcement page. It's under this right here. Hold on. It's under here. This one right here. This one right here was the group work.
Oh, this is quiz. Yeah.
Yeah, it's
Oh.
it's part of the discussion, but I asked it in the form of a quiz. Okay, but yeah, that's that.
Oh, okay. I thought it's different.
No, it's not different. It's basically that.
Okay.
That's
Thank
what
you.
this whole exercise was about.
Mhm.
Okay. Any other questions? Thank
So I
you
have a
for,
question.
yes.
So for clarification, for the molecular geometry,
Mm-hmm.
in order for it to be either bent or non-bent, so for the bent, does the lone pairs have to be on that central atom, or does it have to be, can it be on any other, element
No, it has to be on the central atom.
on the
'Cause
central atom? Okay.
let me make sure that you understand what's going on, because that's what you end up doing in a lot of these things is you're going to end up confusing yourself whenever you're doing molecular geometry. Okay, the only thing that you need to concentrate on is focus on the central atom, because see, like right here, you don't want to focus on that, even though these has lone pairs. That's not going to dictate the geometry. That's only what's dangling in the outside. What dictates the geometry is the central atom. This has no lone pair. Okay, chemicals like these, this has two central atoms. This carbon has 1, 2, 3 domains. That would be trigonoplanar. This oxygen has 1, 2, 3, 4 domains, but 2 of them are bonded atoms, 2 of them are lone pairs. That would be a bent tetrahedral. Bent because it's going to follow this right here. It's going to follow this right here. It's 4 domains, 2 bonded atoms, 2 lone pairs. It's bent tetrahedral. And again, it's because of the fact that there are 4 domains here and 2 lone pairs. But this is a central atom. This is a central atom. This oxygen is not a central atom. You don't count the lone pairs here. You only count it on the central atom that you are looking at. You're basing your geometry around this carbon. You're basing your geometry around this oxygen. So you have 2 answers, 2 geometries. You don't look at these at the end. This oxygen is only got 1, 2, 3 domains. Don't count these. They don't dictate the geometry. Okay, don't count the ends. They don't dictate the geometry. They're just hanging out there. They're flapping in the wings, but it's the central atom that determines whether it's going to be linear, trigonal, tetrahedral, pyramidal. These things at the end do not dictate that. So I hope that's clear.